All right, welcome back. Let's just jump right in. Today, we're going to tackle a really classic tree problem. You know, the kind that looks super tricky on the surface, but it actually has this surprisingly elegant solution. We are going to crack the code on counting Univalue subtrees.
So to really wrap our heads around this, let's think about it like this. Imagine you're looking at a big family tree. Now the real question is, how many smaller family groups, subfamilies, are made up entirely of members who have the same last name or the same eye color? We're looking for those little pockets where everyone is exactly the same.
Okay, so in the lingo of computer science, what we're hunting for is called a Univalue subtree. And honestly, the name says it all. It's just a chunk of the bigger tree, a subtree, where every single node, and I mean every single one, has the exact same value. Simple as that.
All right, let's get our hands dirty with a real example. Here's the puzzle we're going to solve. We've got a tree that starts with a 5 at the very top. That's our root. Now, if you go left, you hit a 1. And that 1 has 2 kids of its own. Both of them are 5s. If you go back to the root and go right, you find another 5, and that 5 has just 1 kid, which is, you guessed it, another 5. So that's the setup we're working with. And hey, just to give you a little spoiler so you know what we're shooting for, the final answer is 4. Yep, there are 4 of these special subtrees hiding in there. And don't worry, by the time we're done, you're going to see exactly how we sniff out every single one of them. So, what's the game plan? Your first instinct might be to start at the top, at the root, and just work your way down. Makes sense, right? But the real magic, the secret sauce to solving this elegantly, is to do the exact opposite. We're going to flip that whole idea on its head and think from the bottom up.
Here's a good way to picture it. Instead of some big boss at the top trying to micromanage everyone, we're going to empower each little node. We'll ask every node to run a quick check on itself and its kids, and then report the results up the corporate ladder. And where do we start this process? At the very bottom, with the interns of the tree world, the leaves.
So what's on this status report exactly? Well, each node has to pass a really simple 3-question quiz. Question 1. Hey, left child, did your subtree check out? Is it Univalue? Question 2. Okay, right child, what about you? Are you good? And the final crucial question, do my kids' values actually match my own? If and only if the answer is a big yes to all of those, can the node send a success report upstairs.
Okay, that's enough theory. Let's get back to our example tree and put this checklist to work. This is where you'll really see why this bottom-up thing is so cool. So, we start at the absolute bottom, the leaves, the nodes that have no kids. And this is kind of the gimme part of the problem, our base case. Think about it. A subtree with only one node, is it Univalue? Well, yeah. By definition, it has to be. All of its one node has the same value. It's the easiest pass in the whole test. And if we look at our example tree, we can spot 3 of these leaves right away. And since every single one of them is a Univalue subtree, boom, we've already found 3. Our counter is already at 3 right out of the gate. Okay. Let's climb up one step to that node with the value 1. It starts its checklist. Are my kids' subtrees Univalue? Yep, both of its kids are leaves, so they already reported success. Check. But then, question 3, do their values match my own? Uh-oh, the kids are 5s, but this node is a 1. That's a mismatch, so this node has to fail its own check and report that failure upwards. All right, let's jump over to the right side of the tree. We see a parent node, a 5, with 1 kid, which is also a 5. Let's run the checklist. Is its child's subtree Univalue? Yes, it's a leaf, so that's an easy pass. Does it have any other kids to check? Nope. And finally, does its kid's value match its own? Yes, 5 equals 5. Everything checks out. We have a winner. This whole little section is a Univalue subtree. And that's a perfect example of our logic in action. Because that little 2-node subtree passed the test, we get to increment our counter. So we add 1 more, and what do you know? We're at 4. And that, my friends, is the final answer we were looking for.
So now for the grand finale, the root node itself, the big boss at the top, the 5. It asks for the reports. The right side comes back, all good down here, boss. Success. But then it looks at the left side, the one that started with that node 1, and that whole branch reported failure. Because even one of its children failed, the root has no choice. It has to fail too. That one no from down below bubbles all the way up and disqualifies the entire tree from being Univalue.
Okay, so we've nailed the logic.
We see how it works. Now for the fun part. Let's see how this beautiful bottom-up thinking actually looks as code. Time to connect the idea to the implementation. So this whole strategy of digging all the way down to the leaves and then making decisions on the way back up, that has a name. It's called a post-order traversal, which is a specific flavor of depth-first search, or DFS. It is the absolute perfect tool for this job. It's like it was made for this. And look at this. You can see how cleanly our simple checklist maps right onto the code. When we said check the left child, that's just the recursive call dfs root.left. Same for the right. Those variables, L and R, they're literally just storing the true or false report that comes back from the kids. Then we have our value check. And if everything passes, we tick up our counter. It's a one-to-one translation of our logic. It's beautiful.
Now this line of code right here, this is the bouncer at the club. This is our gatekeeper. This is the engine of that failure propagation we kept talking about. If that report L from the left or the report R from the right comes back false, this line just throws its hands up and says, nope, we're done here, and immediately returns false up to its own boss. It's how bad news travels fast in a tree.
So, there you have it. We cracked it. But let's zoom out for a second. What's the big takeaway here? What are the key things you should really lock into your brain from all this? First off, when you're faced with a tree problem, always ask yourself, could I solve this from the bottom up? It can often be way cleaner. Second, remember that a node's decision almost always depends on what its children tell it. Third, never underestimate the power of a single false return. One little failure can poison the whole well, invalidating an entire branch. And last but not least, this recursive bottom-up pattern is a powerful tool. Put it in your toolkit because you will use it again, I promise.
And that brings us to one last thought to leave you with. Today, we use this bottom-up search to count something very specific, but think about it. What else could you figure out using this exact same approach? Could you find the height of a tree? Could you check if it's perfectly balanced? What other secrets are hiding in trees that a bottom-up search is the key to unlocking? It's a really powerful